posting the videos and the PDFs with the lecture notes with my notes on them, the slides with my notes on them. So those are on Brightspace. And so the blank slides are just going to be in the lecture notes folder. For any chapter, anything that isn't the blank slides is in the chapter X additional materials. So links to videos, lecture recordings, things like that. Okay. All right. So before we start talking about light and energy, I just thought I'd give you a little Valentine's Day chemistry. So we've got, we have several different chemicals here, and what they have to do with Valentine's Day. Okay, so I'm just going to pick one of them, and I'm going to pick this cute little mouse here. Okay, so this is anandamide. Okay, so if you eat any Valentine's Day chocolate, okay, you will be consuming anandamide. Okay, and it's one of the things in chocolate that makes you feel good and happy. Okay, it's a chemical that has that physiological effect on our body. It triggers the feeling good systems. Okay. However, okay, don't eat too much chocolate when you're studying for the exam, because it is also something that increases forgetfulness. Okay, so stick to Skittles or something when you're studying. Okay. All right. So let's go get started. It's chapter 3. Okay. All right. So we're going to talk about electromagnetic radiation and light and energy. Okay. And then after the first exam, we're going to go into lots of detail about how how having light interact with matter helped us understand how electrons are arranged in atoms. So we talked about the nucleus and the stability of the nucleus and what's packed in the nucleus, right? And so now we're moving outwards, and we're going to talk about what's outside the nucleus. Okay. All right. So in lab this week, again, you are going to be determining, okay, what percent of the mass. Okay, so our goal in lab this week, right, is to find out what percent of the mass of sparkles is actually the element copper. Okay, that's your goal. How are we going to do that? Okay, well, the rock was ground up and it was dissolved in nitric oxide. It was dissolved in nitric acid. Okay, and that causes the copper to go into the aqueous solution. Okay, any remaining insoluble material, okay, was filtered out, and so you have this pretty blue solution. Okay, and how are we going to figure out how much copper is in there? Okay, we're going to put that solution, okay, or some of you have already done this, into a device called a spectrophotometer, okay, that shoots light at our sample, and we measure how much light gets absorbed. Okay, so we know how much light we're shooting at it, and we're measuring how much light doesn't get through the sample. Okay, so as we talk about the electronic structure of the atom, okay, we're going to talk about why, okay, copper atoms, okay, will absorb some of that energy from that incoming light. Why is it that all the light doesn't go through? Okay, not some of the light gets what we call absorbed. Okay. All right, so we've got. So I love this cartoon because it makes a point. Again, that is our theme for today. Okay, is that when we have light, what we call electromagnetic radiation, okay, the different colors of light correspond to different wavelengths. So, different colors, what we call different wavelengths, and we'll talk about what we mean with that. And there's also something called frequency. Okay, so different wavelengths have different frequencies because all light travels at the same speed. Okay? And we're going to link that to energies. Okay? So does that light carry a lot of energy with it? And energy, again, is the ability to do some type of work, okay? In a physics sense, we call it the ability to do work, right? And, just in your personal sense, you know that when you're more energetic, you feel like doing more stuff, right? So, all right, so, hopefully by the end of today's lecture, the joke on this cartoon will make sense to all of us, right? So that, Red Bull, if we think of red light, is going to be a lower energy of light, okay? All right. So let's talk about what light is, okay? So when I say light, I'm mostly referring to either the visible or ultraviolet range of what's known as the electromagnetic spectrum. Okay, so when I say light, I'm referring to kind of a subset of what electromagnetic radiation is. Okay, so electromagnetic radiation, okay, is moving energy. Okay, so this is. So the electromagnetic radiation that comes to the Earth, okay, comes from the sun, right? And it has to travel through space and time to get here, okay? And it travels through what are called electromagnetic waves, okay? And so those waves, okay, have both a magnetic property and an electrical property, okay? So you may have heard the phrase, I've heard it a lot in politics lately, two things can be true at once, right? And so this is true of electromagnetic waves, okay? Two things can be true at once. Their electricity and their magnetism, okay? So sometimes they'll behave like an electrical charge, sometimes they'll behave like a magnet. Okay? And so that energy, okay, travels through space like a wave, okay? And it's an invisible wave, not like a wave on a pond is a wave that's traveling through matter. The matter is the water, right? So electromagnetic radiation, okay, has both an electric component that's shown here in blue, and perpendicular to that, okay, there is what's called a magnetic component. And when you study physics or physical chemistry, that dictates a lot of the math that we talk about when we talk about electromagnetic radiation. But all we need to know for our purposes, again, is the electric part and the magnetic part are traveling kind of at right angles with one another. Okay? And if we are testing kind of the properties of that wave, okay, if we want to know the electric field at any one point in time or at any one position, okay, it's going to look like a wave, okay, a wave in the water that you would see, okay? And so we describe waves, okay, by two features, okay? One is the wavelength, okay? So when we talk about the wavelength, okay, what we're talking about is the distance between two crests Or this is, so the up high part would be called the crest. The down low part would be called the trough. Okay? So our wavelength is really the distance where it takes our wave to hit like one repeat. Okay? So this distance here, okay, is our wavelength. So it's the distance between two crests, or, you know, another way of putting it is the distance it takes the wave to repeat. Okay. The symbol that we use for wavelength is the Greek letter lambda. Okay, so symbol used for wavelength is lambda. Okay. So it's like a little L in Greek. So if you look at the two waves that are shown on this slide, okay, the wave that is down lower, okay, this wave number B, okay, has a shorter wavelength, okay, than the one up at the top. Okay, so if we just took these and compared the wavelengths, right? That one's much shorter. Okay. All right, so wavelength is a key feature of our electromagnetic radiation, and that's going to have there's going to be a direct relationship between the wavelength and the amount of energy it carries. Okay, so I'm gonna give you a little spoiler here. Okay, so shorter wavelengths are going to be traveling with more energy or higher energies, okay? So higher energy waves. Okay? All right. Shorter wavelengths carry more energy. We consider them higher energy waves, okay? And on the next couple slides, we're going to be, reinforcing that, okay? All right. So here is the electromagnetic spectrum, and actually, oh yes, I can, yay. I wasn't sure if the link would work. Okay. That's not what I wanted. Let's see. There we go. That's the one I want. All right. So if we look at the electromagnetic spectrum, okay, it ranges, again, beyond what we can see in the visible, okay? And this is showing you just the region of visible light, okay? So if we look at, if I click on one region, so I clicked on 508 nanometers. It's right here, all right? And you can see what the size of the wave looks like, okay? Now I'm gonna click on something in the purple, okay? And you'll notice that my wavelength is getting shorter. As I go further to the red, okay, it's getting longer, okay? So, blue light to red light, the wavelengths get longer, okay? All right, so you'll notice, okay, that there are two other kind of features that are provided in addition to the wavelength, okay? Now, when we're talking about the wavelength of electromagnetic radiation, what unit is being used there? Yeah, Ben.
Talking about the
Yes. Nanometers. Okay, so let's talk about the size of an electromagnetic energy wave. All right, there we go. All right, so 448 nanometers. So I'm going to use my metric prefixes to turn that into scientific notation. Okay, so nano is 1 times 10 to the minus 9, okay? So this is going to be 448 times 10 to the minus 9 meters, okay? So that should give you a sense, of the size of these electromagnetic waves. You are not going to, it's not like, again, seeing a ripple in the water, okay? The wavelength is very, very, very small, okay? But, again, as I go to, let's go back here, and let's go to one of these long red ones, okay? Whoop. Okay. You'll notice, it's, again, the wavelength is longer. It's about 705, okay? So let's just say red light, about 700 nanometers, okay? So if we want to think of that in, just in meters, okay? So if this is 700 times 10 to the minus 9 meters, so let's do our 1, 2, 3, 4, 5, 6. So if we move this, right, 9 places to the left, so that's 3, that's another 3, that's another 3, okay? So this is 0.000007 meters, okay? All right. Oops. Okay, so let's look now at these other two things as we move around, okay? So moving towards red, what happens? Wavelength gets longer, okay? Okay. All right, so let's go back and we'll see what happens to something called frequency, okay? So I'm going to start in the blue here. And we'll see our frequency is 7.36 times 10 to the 14 hertz. And I'm going to go to the red. Does my number get bigger or smaller for the hertz? So 7 times 10 to the 14, 4 times 10 to the 14. So as my wavelengths are getting longer, okay, my frequency is getting smaller, okay? So let's talk about what frequency is, okay? So frequency, I'm going to say decreases, okay? All right, so if I just, say I eat chocolate frequently, what do I mean? Yeah, in a given amount of time, in a day, how many times I eat chocolate, right? So when I'm using the word frequency to apply to waves, okay, it's going to be how many of those wavelengths, okay, how many crests will pass by would pass by a point in 1 second. So a hertz is a unit of per second, okay? So 1 hertz equals 1 per second. It's also called, second to the minus 1, because the minus 1 exponent means 1 over something, okay? So that's what a hertz means. So the frequency is how many waves can pass by a point in a given amount of time, okay? So frequency Okay. So that's our frequency. Yeah.
So is hertz the measurement?
Hertz is the unit that we use, okay? And saying 1 hertz is the same as saying 1 wave per second. Okay? Does that make sense? So what that means, right, is that this thing here, okay, if I was watching, let's say I was watching this, if I was able to watch that point on the wave, okay? And I watched it for, a minute, okay? What would happen is I would have a certain number of those points pass by me, okay? And if I figured out how many of those points passed by per second, okay, then I would get the frequency of the wave, okay? Now, these numbers are 10 to the 14th, right? So what does that imply about the speed of electromagnetic waves? Are they fast or are they slow? They're very, very fast, okay? So this is going to lead us to the speed of light, okay? Again, light is electromagnetic radiation. And in sci-fi movies, when they talk about, traveling in space, right? You sometimes hear the speed of light mentioned, right? And so light moves very, very fast, okay? But things with longer wavelengths, okay, will have fewer of those wavelengths pass by. Okay? All right, so the last thing that's kind of on this slide is energy. Okay, so I'll switch to green here. Energy is expressed here in unit of joules, okay? So there's two, when we study, in general chemistry courses, there's generally 2 energy units that we use, okay? We tend to most frequently use the joule. It's a unit that we use to measure a certain amount of energy, okay? One that you're familiar with, okay, is the calorie, okay? So calories in a dietary sense are 1,000 calories in a chemical sense, okay? But so a calorie and a joule are units used to measure the same thing. They're just a different size, okay? All right, so joules, okay, let's look at how the energy changes. Okay, so when that number gets bigger, reload this. There we go. All right, so we'll start with our high frequency, small wavelength over on the left, right, our purple. Okay, and this time we're going to focus on what this photon energy number is, okay? All right, so it's 4.97 times 10 to the minus 19 joules. Now let's go red. We've increased the wavelength, decreased the frequency. What happened to our joules? It's still 10 to the minus 19, right? All right, is the number before it bigger or smaller? Smaller, okay? So as we move red, okay, less energy is carried by the wave, okay? So let's go here. So moving towards red, energy decreases. All right, so moving around in the visible spectrum gives us the relationship, okay, between wavelength, frequency, and energy. These trends hold for the entire electromagnetic spectrum, okay? So if we go into things like microwaves, gamma rays, X-rays, okay, you've heard of all these things, right? You use your microwave to cook your food. You use X-rays if you broke your bone or if you go to the dentist, okay? And those are just electromagnetic radiation with different frequencies, different wavelengths carrying different amount of energy, okay? But those wavelengths cannot be detected by the human eye, okay? So my cat Waffles, okay, there are some colors that she doesn't see as well as humans do. But cats can see further into the red. So this, There we go. So the visible spectrum, okay, is very anthropocentric, if you will. It's very human-centered, right? This is what we can see with our eyes, okay? But there are molecules in a cat's eye, okay, that can respond to electromagnetic radiation that's over here, okay, that we can't see with our eyes, but we can feel it as heat. Okay, so they can see heat. You know, it's like having night vision goggles. You can, if you put those on, you can see the heat that's emanating off of a living thing, okay, or a hot surface. All right, so again, we have this kind of direct, yeah.
What does it mean by photon?
So we're going to talk about that now, okay? So when we talk about light moving, so this is the other really funky, weird thing about light, okay? We said it's electric, it's magnetic, okay? It also acts like it's actually a particle, like it has mass sometimes. It's just very weird, and this is the whole quantum mechanics thing, like why people consider Einstein so great, because he was able to think of this explanation that just doesn't make any sense when we're thinking about macroscopic physical things, okay? So photon, okay, is what we consider 1 unit of light energy, okay? So if we wanted to describe a photon, okay, we would describe it by its wavelength, a photon of 480 nanometers wavelength. And then that would enable us, okay, to know something about its frequency and its energy, okay? Now, the reason that we can do that, okay, is if we were to do a completely full exploration of every little wavelength and what its frequency was, okay, what we would see, okay, is that there is sort of a direct relationship, okay, so between the frequency and the wavelength, okay, and that relationship is the same for every color of light, okay, which indicates to us that all light is traveling at the same speed, okay? All right, so all electromagnetic radiation, whether our human eyes can see it or not, okay, travels at the same velocity, okay? So this is just speed in a particular direction. So if you're a physicist, you know, it's not enough to say how fast something is moving. You have to say what direction it's going in, and we call that a velocity, okay? So if we put our electromagnetic radiation in a vacuum, okay, do you know what I mean when I use the word vacuum? What does the word vacuum mean to you? Yeah, Ben.
So it doesn't contain like a medium like water, oxygen, air, any particulate matter that could potentially slow down the photons.
Exactly, okay? So when we say vacuum, okay, what we're talking about is we are talking about an environment where if there's a perfect vacuum, there are no molecules present. There is just empty space, okay? So vacuum. So perfect vacuum is empty space. There are no molecules whatsoever, okay? So, you know, when we use a vacuum, whether it's, you know, vacuum our carpet or whether it's in the lab when we're applying a vacuum to something, what we're doing is we are sucking the matter, we're sucking the particles out of whatever vessel, you know, we're applying the vacuum to, so that hopefully we'll be getting as many of those molecules, as many of those particles out. So if you have, again, and Ben made a good point, that if you have a vacuum, okay, so there's nothing there that the wave is going to bump into. So if we measure the speed of different electromagnetic waves, different wavelengths, different colors of light, different frequencies, they all travel at the same speed, okay? And that speed is really super fast, right? It's 3 times 10 to the 8 meters per second, okay? So this is what's called the speed of light, okay? And again, because we noticed, okay, that when we're looking at light, okay, and we're looking at its frequency, okay, and its wavelength, there's always this kind of same direct relationship, okay? We can derive an equation that kind of predicts what my frequency is going to be given my wavelength, okay? So here is the relationship right here, okay? So the product of my wavelength and my frequency is always going to be the speed of light, okay? And so do you remember our trend? The longer the wavelength, the lower the frequency, right? So the bigger the one number becomes, the smaller the other has to become. And they do that in such a way that their product always winds up being the speed of light, okay? So they have to vary in that way for the wave to be traveling at that speed. All right, so we can figure out, again, what the frequency and the wavelength of our light are, because we know the speed of light. This is a constant. Okay, it never changes. And again, it's very, very, very fast. Okay, so, does anybody here like astronomy or just like looking at the constellations or the stars? Anybody? Yeah. So one of the things that they'll say is like, if you look and you see, a galaxy or a planet or a star somewhere, that like the light that you're looking at, the light that you see is from, thousands of years ago, okay? And that's, because we know how far or how fast light can travel, okay? We can get a sense of the distance of celestial objects, okay? Because of that constant, okay? And it also gives you a sense of how far these things are. If it takes light 1,000 years to travel to Earth, okay, it must be super, super far, because light travels, almost 1 million meters per second, right? All right. All right. So let's spend the rest of class today just doing a few examples. Okay, so who listens to WONY? Who knows what WONY is? Okay, WONY. What is WONY? It's the campus radio station, right? All right, so this is... Does anybody know... Whoops, let's spell station right. All right, does anybody know if you wanted to dial up on your FM dial, you're dialing frequencies, right? Right, so what is WONY's frequency? 90.9. It's 90.9, right. Do you know what the units are on the FM dial? I think it's megahertz, right? So if we go, if we go back to chapter 1, let's go zooming back. Does anybody remember what mega is in terms of prefixes? Mega is 1 times 10 to the 6th, okay? So that's going to be the frequency that we're working with. Okay, so, all right, so 90.9 times 10 to the 6th hertz, okay? So if our relationship, right, between wavelength and frequency, okay, is C equals lambda nu, and I realize that I did not tell you what we use as the abbreviation for frequency. Okay, so nu is frequency. And that's the Greek letter called nu. Okay. And c is our speed of light. Okay, right, which is 3 times 10 to the 8th meters per second. Okay. All right, so what we want to know is what the wavelength is. Okay, so we have to solve this equation for the wavelength. Right? So let's go here, and we want to solve for the wavelength, which is lambda, right? So just not to make any assumptions, I'm sure you all can do the algebra, but remember that to solve this for lambda, we have to somehow move the nu over to the other side. So what we do is we divide both sides by nu, right? Because you can do the same thing to both sides of an equation. Okay, so that means that the speed of light divided by nu is going to be equal to lambda, because when we divide by nu, that cancels out, right? Okay. All right, so we've got 3 times 10 to the 8th meters per second divided by 90.9 times 10 to the 6th hertz. If I want to put that in units of seconds, so I have some unit cancellation, okay, this is going to be per second, right? Okay. So what's going to happen, right, is I'm going to have meters per second divided by per second, which means it flips, okay? And so the seconds are going to cancel the units, okay? And even if that math is not obvious to you, we know that lambda has to be in wavelengths, right? Or that lambda has to be in meters, right? Okay, so what do we get in terms of meters? Let me grab a calculator. So we've got 3 times 10 to the 8th divided by 90.9 times 10 to the 6th. And we get 3.3 meters, okay? So which direction, okay, let's go back to our rainbow visible spectrum, okay? And let's put WO on Y on this scale. Which side is WO and Y going to be on? Is it going to be on the right, beyond the red, or is it going to be on the left, beyond the purple? So, let's look here. 448 times 10 to the minus 9 meters, right? So that's over here, times 10 to the minus 9 meters, right? This was also times 10 to the minus 9 meters. This, we got an answer of 3.3 just plain meters, right? Very long. Okay, so where are radio waves going to be? They're going to be beyond the red, okay? So radio waves are going to be somewhere way over here, okay? So, and that's where we want them to be. So next class, we're going to talk about energy, right? And how short wavelengths carry a lot of energy, and a lot of energy can do damage to matter. So if we're bombarding the airwaves with radio waves so that we can listen to, our favorite music or the news or whatever, okay, we don't want it to be really high energy stuff that's going to damage you if you're sitting in your car and you're listening to those, those waves, right? So they're very long wavelengths, makes them good for traveling over long distances, okay? And they're low energy, right? So before next class, okay, try to do those 2 other examples, and we'll start off by quickly going over those, and then we'll get into talking about energy and how that tells us about atomic structure.